Cool. Thank you for being here. I'm Rahul. I'm the founder of Aerius Labs. And today, in some haphazard manner, I'm going to talk about how to build scalable end-to-end private voting protocols. And we'll try to reduce the cost to the end user to approximately zero. So our mission is to empower DAOs, organizations, and whatever the state of the art in voting protocols is, to make them make important decisions with privacy and integrity. So if you consider current state of the art, probably everyone uses one of either of the existing solutions today. And I've been a DAO member of a variety of DAOs, done voting there. And across time, I saw a variety of different problems, which was obviously centralization risk. A lot of these protocols exist on trust assumptions in the sense that snapshots of eligible voters, so eligibility sets are completely generated by these protocol servers themselves. There's the bandwagon effect. Lack of privacy in voting leads to a certain psychological phenomena, which is deemed as the bandwagon effect. And it simply means that people tend to vote or follow whatever's the most popular, right? Say if I'm holding a DAO vote today for Aave, and there are 90% of the votes in favor of yes, and suddenly Vitalik comes in and gives an argument against whatever the favorable vote is right now, most people would shift their votes without even considering without making their own opinion. So that's the bandwagon effect, and obviously privacy has different concerns as well, because it can lead to coercion. I can always take a hammer if I know if there's a Paul in this audience. If there's Paul, and I personally know Paul, and I saw his address vote against my protocol, against my proposal, I can always go in and whack him in the head with the hammer, and then from the next time, he will be, well, in a sense, convinced to either not vote or vote in my favor. So this is the Malk DAO report, and this is what the state of the art exists, and what features or guarantees different voting protocols give you. Out of these, if you can see, the Aztec Aragon solution is the best one. However, it lacks one thing, private protection, which today only Macy is able to provide. We will try to build a protocol that will, over the next 7 minutes, that will try to give all those guarantees from Aragon and Aztec. However, we will try to bring down the end user cost for each user down to approximately zero. So we termed this ZkSnap as, let's say, a bastardization of Snapshot, ZK version of it, just a name. So the first step is user privacy, right? User needs to remain private. They need to be able to prove that they're part of some membership set, and they should be able to prove how much voting weight they hold in a certain DAO. So the easy solution is build a commitment, a Merkle commitment to it, and then a user can simply create Merkle proofs. However, that's not so great, because you come back to the same problem of who creates this Merkle commitment, how do we trust them? And no user is going to iterate over all members of the DAO and try to recreate the membership set to verify that it's correct. So what we do is we leverage storage proofs. We try to use the blockchain as an arbitrary lookup database, and then we can define arbitrary predicates on these and define membership sets based on that. So membership set could be, a user says, I was an LP in a specific Uniswap pool over 1,000 blocks from after block 10,000, right? I should be able to prove that. However, there's no way to prove that from just a Merkle commitment. And then we need to be able to stop users from being able to vote again and again So basically stop a double spent vote. So we need to use a nullifier for that case. Plume comes to mind, especially when building on Ethereum, because it's state of the art for using ECDSA signatures to create, using ECDSA public keys and private keys to create deterministic signatures that can act as nullifiers. In fact, one of the authors of the paper are presenting today for ZK Mail. However, Plume, writing Plume in circuit is fairly expensive. So can we do better? So usually, Plume makes the assumption that the message can or cannot be random. However, if we constrain the system to a certain degree, we could potentially get away with this, right? And what we do, using existing, wallet tools that are out there. So what we do is instead, assuming that every time for a specific proposal, a unique message can be created, a user can sign that message, so that's the signature. They can append that message to their signature, the concatenation, and hash the whole thing, and this will create a deterministic nullifier for them, and it's extremely cheap. So using Spartan ECDSA, they've already shown that verifying ECDSA signatures can be as cheap as 4,000 or 5,000 constraints, and suddenly we bring down the cost from hundreds of thousands of constraints to a few thousand constraints, which is okay, because at the end of the day, the entirety of the user proof needs to be created in the browser. The second thing that we need is ballot privacy. So the ballot should remain private, and no one should be able to see the running vote while the protocol is still going on. So usually El-Gamal comes to mind because if you encrypt it into the encrypt a value to the powers, you can just multiply the two values, and you should be able to do addition over over these encrypted values. However, you need a lookup table for it, and especially if voting weights if you talk about Ethereum, voting weights, if we use them by token balance, they can be as large as the largest value of a U256. Which is not great, right? You can't have a lookup table that great. So maybe we can use something else. In this case, we use the Pallier crypto system, pioneered by Pascal Pallier. And Pallier allows us to do addition over encrypted text in a very cheap manner, using just a few multiplication and modulo operations. Cool, so as long as I have encrypted my values and I give my encrypted vote to someone, let's assume this to be a semi-honest party, they should be able to take two users' votes and add them together to create whatever the running tally of the ballot is going to be. And we should have an encrypted ballot that no one can see. Now, the problem comes out to be who decrypts this ballot, and how do you make sure that no one withholds the data or what the ballot's value is once the voting period ends. So we use something called time-locked encryption or delayed encryption, and basically the private key used for the homomorphic encryption, we encrypt it using time-locked encryption at the start of the protocol, and then we keep a running tally for using running tally of the ballot using homomorphic encryption, additive homomorphic encryption, and at the end, because we've defined the voting period and the time lock encryption of the private key to be the same, as soon as the voting period ends, the private key becomes public, and anyone can just simply pull the current encrypted ballot and see what the final results are. We also want succinct verifiability, and also we don't want retroactive attacks, which is once users' proofs should not be public at the end, such that if I have 10 users' proofs, and once the private key becomes public, I can decrypt their balances, although their identity is still anonymous, I can do a statistical analysis attack and still be able to figure out who voted what. So we use recursive snarks, going back to our semi-honest person aggregator. As long as we assume that they're censorship resistant, they can continuously keep on rolling up these proofs, and then you have a final proof that gives no other information other than whatever the final ballot vote is, and it also gives you succinct verifiability in the sense you have a Groth16 or KZG-based proof at the end, which you can verify on Ethereum. So a single proof gives you the validity of the entire voting protocol. I'll quickly walk over what the application workflow looks like today. Before the encryption, we encrypt the secret via TLE. We provide a reference block number for the storage proofs. We provide an encryption election ID and some certain combination of plain text with election ID forms our unique message for our deterministic nullifiers. The election duration, which is used to encrypt the private message, and the encryption public key that is made public at the very start so the users can vote. During election, you have the aggregator. This is our semi-honest aggregator that keeps on taking user proofs, rolls them up in a single proof, and at the end, you can put this final proof anywhere for the users to be able to verify. You can put it on Ethereum, you can put it on IPFS, you can put it on IPFS so that all users can pull it, and then put it on Ethereum for verifiability as well. And after election, the results are published, and anyone can simply pull the private key from DRAND, and they should be able to decrypt the ballot and see what the final vote is without any other information being leaked. This is what the circuits look like. User provides signature, vote weight, salt, storage proofs as private inputs, and all the other stuff as public inputs, and then you create a proof. Aggregator takes the user proof, so we use IVC in this case. So, you can think of it as induction-like proof aggregation. In the sense they take the preceding aggregator proof, verify it, take the current user proof, and aggregate it to a new proof. Future improvements are going to be to add fully homomorphic encryption, multiple voting modes. In fact, fully homomorphic encryption would allow us to enable multiple voting modes because we won't be restricted to only addition anymore. We can have quadratic voting. We can have weighted voting with linear backoffs or something else. And obviously one single thing that still escapes this protocol, and including Aragon and Aztecs, is anti-collusion. Is something that we need to take care of because the user could still create a public version of the same proof, and I could have a smart contract where I give both the proofs, public and private, and as long as the public proof proves to me that a user voted in a certain way, I release some funds to them, and then they submit the one with private inputs to the aggregator. Thank you. You can scan this to access the white paper and a form to join the alpha waitlist for the protocol.
Cool, thanks a lot. Do we have any questions?
Thank you. I have a question. Do you achieve everlasting privacy? In other words, how do you prevent individual ballots to be decrypted after the voting?
Yes, so this is why I said the aggregator needs to be semi-honest in the sense they would not leak individual user proofs later on. So this can be implemented using multiple methods. You can have it as a TEE, or it could be an MPC-based network, or something else. You could also have, encrypted witnesses and use those to generate the recursive proofs. So again, it's a trade-off space. You can pick one or the other. However, you do need a semi-honest aggregator in order to do so.
Okay, thank you.
More questions? Maybe the next speaker can already go on stage and set up.
Could you explain how you use nullifier to not let people vote twice?
Yes. So let's just take the example of Plume. Plume allows you to create a deterministic nullifier that ties a user to their public key. And because it's deterministic, a user, whenever they create it again, it's going to be the same nullifier, right? Which means if I add it to an append-only nullifier tree, I can always I'll have to provide a proof of non-inclusion in order to vote. And if a user is unable to do so, that means their vote is not valid.
Okay, so let's thank Rahul again.